Hello grade 12s, this is physical science. My name is Gillian and we are going to consolidate what we have learned about optical phenomena. We're going to look at some questions that are of an exam standard and we're going to unpack them and see how to answer them. So let's go to the first one. It says here, question 1, an experiment is conducted to investigate the relationship between frequency of incident light on a metal. So, frequency, there we go, of incident light on a metal. And the maximum kinetic energy of emitted electrons from the surface of the metal. So, we've done this before. So we've got a metal surface there. There's our metal surface. We have got incident light hitting it. It is going to have a frequency, that light, and then electrons are emitted from the surface. This experiment is conducted for 3 different metals. If you remember back to what we've done before, each metal is going to have a very specific frequency of light at which electrons can be emitted from its surface. So different metals, you're going to get 3 different results. The graph below represents the results obtained. So let's check out that graph. And we can see here that the metals that they are testing are potassium, zinc, and platinum. They are different lines, and the reason why they're different lines is because they are a unique metal, and each unique metal requires a unique frequency of light to be able to eject these electrons. On the y-axis, we have got maximum kinetic energy. On the x-axis, there is frequency, and that tells us it's times 10 to the 15 hertz. And then over here, there's a minus x. How's that? That's interesting, isn't it? Let's see what that's going to bring us. Let's first answer the first question. 1.1 says, name the phenomena on which this experiment is based. Well, we are talking about electrons that are being forced off or bounced off the surface of a metal. We're talking about light behaving like a particle. It's particle behavior. And so this is called the photoelectric effect. So let's write that in. It is the photoelectric effect. That proves to us that light has a particle nature. Now, the next question is a tricky question. Name the physical quantity represented by x on the graph. So now we need to delve into our mathematics knowledge. So when we're dealing with a straight line graph, I think we have, let me write this down, well maybe you can remember, y is equal to mx plus c, that formula. What do we have on our y-axis? Well, we have on our y-axis this thing here, maximum kinetic energy. So, EK max. What do we have on our x-axis? We have got frequency. Okay, so there we've got frequency. What about this plus c? Well, that is where the line cuts through the y-axis. So that would be this x value here. It is for potassium. So you can see potassium, the line moves through in that direction and it cuts at x. We know we've got an equation that looks like this. E is equal to work function plus maximum kinetic energy. So what do you think that x value is going to be? Well, it's going to be the work function. These are all related to one another, and that equation, the energy of a photon equals work function plus the kinetic energy, the maximum kinetic energy of the electron, is telling us that x value is the work function. That is quite a lot of science work and maths work to do. But once we have done it and figured it out, it all makes sense. That was quite a tricky one. Okay, next one. Which one of the three metals needs incident light with the largest wavelength for the emission of electrons? And give a reason for your answer. So let's read this question again. It's always good to read questions at least twice. Which one of the three metals needs an incident light with the largest wavelength for the emission of electrons? Isn't that strange? They're asking about wavelength. But we have been given information which is about frequency. Let's have a look at this graph again. I'm going to turn back to the graph. We have been given information that is about frequency, and now they're asking about wavelengths. What is going on? If you remember back to speed of light, you will know that the speed of light is equal to frequency times lambda, times the wavelength. So frequency and wavelength are interlinked. So if we increase the frequency, the wavelength is going to decrease. If we increase the wavelength, the frequency has to decrease. So they are linked. They're not asking us about frequency, they're asking us about wavelength. So the question is, here, the largest wavelength. What is the largest wavelength? That means that it has to be the smallest frequency. So which one of the three metals needs, in other words, the smallest frequency to emit electrons? Let's look at our graph, and we can see along here, our x-axis is frequency. The smallest frequency is going to be this one here. So it is potassium. Our answer is potassium. Isn't that an interesting way of looking at things? So don't let that confuse you. You need to remember that wavelength and frequency are linked to one another. So our answer here is going to be potassium. Now it says, explain. Explain why you have chosen potassium. There are a number of answers that you could give. I've given you 3. So you could say that potassium has the lowest work function. You could say that it has the lowest frequency threshold, so the lowest threshold frequency. You could also say it has the highest threshold frequency because our wavelength, threshold wavelength, and threshold frequency are linked. Our next question. Define the term work function in words. So remember, work function is talking about the electron's point of view. Frequency is talking about the light point of view. So what about the electrons? What do they need? Work is telling you that it is about energy. So in terms of electrons, it will be the minimum amount of energy needed by the electrons, so energy required or needed by the electron on the metal surface, so on the metal surface, to be ejected or emitted, to be ejected or emitted. You can also say the word emitted from the metal surface. Grade 12s, it is time to have a break. When you come back, we're going to solve some other problems. Hello grade 12s, we're back from the break. We're continuing with these exam type questions and how to answer them, optical phenomena. So the next question requires some thought. So let's have a look at it. They're asking us to calculate the work function of platinum. So calculate the work function of platinum. Here it is here. Work function is W0. Now, work function is the minimum amount of energy that an electron requires to be ejected or emitted from the surface. It is the amount of energy needed to move it from just below the surface to just on the surface. Is there any kinetic energy? No. That electron is not moving off the surface, it is just moving from below to onto the surface. So when we are thinking about this, we need to bear in mind that for this situation, the EK max of the electron is going to be 0. So we've got two ways of solving this problem. We can either use this formula, which we know about, which is using Planck's constant times the threshold frequency, or we can use this equation at the bottom. If we use this equation at the bottom, we need to know that this value over here is going to be 0. Why? Because for a threshold frequency and for a work function, that electron is moving just from under the surface to just on the surface. This would be the more reasonable equation to use because it involves a smaller number of values to substitute into the equation. So let's do that. From the data sheet, you will find Planck's constant. So this H is Planck's constant, Planck. And we will substitute in 6,63 times 10 to the minus 34. And then what about the frequency? So we're talking about threshold frequency. We are only given information on the graph. So here we go. If I look on the graph for platinum, I can see, sorry, there's platinum over there. I can see that value. That is where it cuts the x-axis, and that is my frequency. I have to read that off the graph. I've got 1.5 here. I've got 2.0 here. So what is the increment of frequency? It's going to be 0.25, and so that value there is 0.75. I substitute that in, 0.75 times 10, make my times look a bit better, times 10 to the 15 hertz. Okay. And then I can calculate that using my calculator, and I end up with 1,160 times 10 to the minus 18. And remember, we are talking about energy, work, function. Work is telling you it's about energy, so that's going to be in joules. I can use the second one, again substituting in all my values, but for EK, I'm going to substitute in 0. Okay, that's quite That feels quite a successful feeling. You get quite a successful feeling when you know that you have calculated something and thought it through nicely in your head. Right, the next question. Frequency of the incident light that will emit electrons from the surface of platinum with a maximum velocity of this. So that's what we've got to calculate. The frequency of the incident light. We know what the threshold frequency is. That has been given to us. If we look at this graph, we can see it. Our threshold frequency has been given to us. It is 0.75 times 10 to the 15 hertz. But that's not going to allow electrons to be emitted. So, right off the surface with a kinetic energy. So, we want to find what is that frequency that's going to give us electrons being emitted from the surface at 5,6 times 10 to the 5 meters per second. It is velocity. Where do we have velocity in an equation? Here it is. We start off with our original equation. There it is. EK maximum is a half mv squared. We want to calculate this frequency here. Can you see that? If we don't want the threshold frequency, we've got that. We want to know what frequency does the light have to be to emit this electron from platinum at this particular velocity. And all we have to do is substitute in our values. So I'm going to start on this side. H is Planck's constant, so it's 6,63 times 10 to the minus 34. F is what we want to find. We have already calculated this value, which is W0. It is the work function. We've already calculated it. We don't have to substitute it in again because we know what it is. And from our answer, it was 1,160 times 10 to the minus 18 joule. So we know that. Let's substitute in for the formula of kinetic energy, and we have to look up on our data sheet the mass of the electron. So the mass of the electron is really, really small, and we're going to write it in 9,11 times 10 to the minus 31. See how tiny it is? And what is the velocity? Well, they've given us the velocity, and that is 5,6 times 10 to the 5. Now, be careful here. Our formula says a half mv squared. You need to square that value. Once we have substituted all our values in, a lot of them come from the data sheet. Be wary, be careful. Copy down from the data sheet correctly, and then use your calculator correctly to find the answer. So once we have calculated all that, this moves to the opposite side. So we divide by this Planck's constant, 6,63 times 10 to the minus 34. What I'm going to do is I'm just going to erase this on this side so we don't get confused about it. So I'm just going to erase that. You know that we've moved it over so that we can calculate this value of frequency that we need. And once we've done that whole calculation, we end up with an answer of 1,97 times 10 to the 15 hertz. Now, let's just check our answer. We know that the frequency, which is threshold frequency, is 0.75 times 10 to the 15. Okay, there it is there. 0.75 times 10 to the 15 hertz. Let's have a look here. Sorry, not 0.75, 1.75. I'm not reading my own handwriting correctly. So it's 1.75. Have a look at my answer over here. 1.97. Is it bigger? Yes, it's bigger. Is that what we need? Yes, that's what we need. We need a bigger frequency in order to expel those electrons at a maximum kinetic energy from the surface of the metal. So yay, that is a good, well-answered question. We have time for one quick one. It's a different kind of question, and I like it because it is exposing us to different types of questions that we are asked. So here we have a potassium metal plate is irradiated. In other words, it has light that is being shone on it with a light of a wavelength, and there they give us the wavelength of 5 times 10 to the minus 7 meters. The threshold frequency of potassium is that amount. Okay, isn't that interesting? This you might remember as being an external circuit set up and electrons being moved or being ejected from the metal surface, and then the electrons move towards the opposite plate, and we can then get a reading on the ammeter showing that a current is flowing. There is a threshold frequency though that is given to us, and we need to bear that in mind. Okay, so what is the question? Define the term threshold frequency. So frequency is about the light. Work function is about the electrons. So what is the threshold frequency? The threshold frequency is the minimum frequency of the light in order to emit electrons from the surface of a metal. Now, calculate the energy of a photon incident on the metal plate. That's interesting. So here's our photon. We have to calculate the amount of energy that it is carrying. We know that we have been given the wavelength. Let's check the question again. Where's our wavelength? Our wavelength is here. The wavelength has been given to us as 5 times 10 to the minus 7 meters. So we have a wavelength. So what kind of energy will that photon hold? So this is 5. So let me just check it back again, just so that I get it right. 5 times 10 to the minus 7. 5 times 10 to the minus 7. So that is information that has been given to us. What do we know about the energy of a photon? We know that its formula is this. Energy of a photon is equal to Planck times frequency. Do we know what its frequency is? No, we've only been told the threshold frequency of potassium. We don't know. But what we do know is that the speed of light is equal to frequency times wavelength. We know the wavelength. If we rearrange that equation, we get frequency is equal to speed of light divided by wavelength. We have it. So energy then for this calculation is going to be equal to Max Planck's constant times the speed of light divided by the wavelength. I'm going to substitute in quickly for you, and that will be 6,63 times 10 to the minus 34. You get that off your data sheet. Speed of light, also from the data sheet, is 3 times 10 to the 8 divided by the wavelength, which is 5 times 10 to the minus 7 meters. Right, we are going to call it a day there. Please have a look on the site, on the platform, for the answers to the rest of these questions, and I hope that you are now able to use your data sheet to see what values you need. I hope you are able to manipulate formula so that you can find the correct answer. Good luck, grade 12s. We will see you next time.